Okay,
Hi. Okay. Assalamu alaikum, everyone. Welcome to today's online conference covering a dive into the field of NeuroAI.
okay, the speaker seems disconnected, but I can take care of it from here. Hello, everyone. I hope you're doing great. My name is Imane Hamzaoui, and I am a research assistant at NYUAD, and I will be presenting today my work on the field of NeuroAI. I hope that he can join us in a minute to change the layout. Okay, let me just let them know that there has been a disconnection.
Okay. Salam once again. I'm sorry. I have a quick electricity cut. It's out of our mind,
Oh,
so
okay.
for the technical for the technical issue. So again, we are honored to have our speaker today, Imane Hamzaoui, an AI researcher whose work focuses on neuro AI. Imane, the stage is yours.
Okay. Thank you so much for joining again, and it's fine, it happens. I hope you can see my screen. And first of all, I'm thanking you all for attending today's talk. And today's talk is going to be called A Dive into the Field of NeuroAI. So this presentation is inspired by a presentation given by Martino Sorbraro at Trent Camina, which is computational neuroscience and machine learning in Africa. And they host this summer school every year. So if you're interested in the field of computational neuroscience, you can apply for future editions, inshallah. So I'm going to start by introducing myself. I'm Imane Hamzaoui. I'm currently a research assistant at NYUAD, and I've been part of School of AI for years now. I've obtained a master's in engineering degrees in computer science, specialized in intelligent systems and data at ISI Algiers. And I did my final year internship at New York University, Abu Dhabi, and where I worked on exploring the potential of fruit fly and brain-inspired neural networks, but not solely fruit flies, but I did work on the human brain as well. And my recent research interests revolve around neuromorphic computing, in-memory computing, neuro AI, and deep learning in general. So let's start with a bit of background with machine learning and then switch to the other side. So maybe I don't need to ask this question, but why do we need machine learning? Well, for many applications that we use it in our everyday lives, the simplest example is image classification, image detection, image recognition. And the best example I could give in this scenario is actually the university dorms that use it, use facial recognition to let us in. We have image segmentation, which means finding certain segments in the image, and the most obvious, or like I think one of the most useful applications of this is in medical applications. Here, for example, you have a brain that has a tumor, and we use segmentation to detect where the tumor is and the different levels of this tumor. We have the green one is the edema, um, yellow one is the advancing tumor, and other characteristics as well. Another application or technique would be reinforcement learning, and it is mostly used in robotics applications. And we have natural language processing and language models such as ChatGPT and other techniques. So as you can see, deep learning has revolutionized various domains from computer vision to natural language processing to reinforcement learning. And some people would say that we don't need machine learning for a lot of scenarios, but I would say I like this example. You can see here letters in Georgian and letters in Tibetan. I can see a bit of difference between the two letters, but if I show you this and tell you which one is Georgian and which one is Tibetan, then good luck in recognizing them if you're not familiar with any of them. I might guess a little and say that this one is Tibetan, this one, and these two ones are Georgian. But it is actually, I made a little mistake. This one is actually Georgian, and I said Tibetan, and the evaluation accuracy is 80% on our test set. And one of the questions many people don't ask is when not to use machine learning. At some point, it became just a hype, and we try to use it everywhere. It's good, it's performant, but there are many scenarios when we should consider using other things. So, do we need a machine learning model? Can we not use a model based on real theoretical understanding of the subjects? If the task is very simple and if and else can solve it, why choose a full ML model? Do we have enough data available? Because machine learning is very data hungry. And are the data stationary and complete? Because generalizing is hard and risky. And what performance guarantees do we need? Is it okay only to have statistical guarantees? For example, some people might use accuracy everywhere, while we should consider other metrics such as recall and precision. Do we need interpretability? Because machine learning methods usually are black box and don't provide explanations for their decisions. And there are ethical concerns related to this. And if I ask you, what's the largest neural network you know? Some of you might say it's a ResNet. A ResNet 152 has 60 million parameters. Some of you might say GPT. GPT-3 has around 175 billion parameters. GPT 4.5 is estimated at around 1 trillion parameters. And let me tell you, the brain, this very simple organ, well, not simple, but small organ, contains about 80 to 100 billion neurons that are connected to each other by more than 100 trillion synapses. Synapses means connections, and that's 10 to the power of 14, which is huge. And who would have imagined that we would have that much connections in this small um, volume? And each one of these neurons is a lot more complicated than a ReLU. I suppose you're familiar with what's a ReLU. A ReLU is an activation function, and the tiny worm C. elegans, C. elegans is a tiny organism, exhibits complex behavior with just 302 neurons and 7,000 synapses. So we can see advanced intelligence with just this much neurons. And if I ask you to train a neural network with this size, then on a complex task, then maybe it will not perform very well. And this has driven. This is why in my master's thesis I explored using the fruit fly brain, because it has around 1,000 Kenyan cells, but it performs very, very well on certain tasks. So let's talk a little about neural networks and biology and machine learning. Where does this all stem from? The picture here is a picture of a real neuron, or like a drawing of it. And a real neuron is characterized by a tree structure where the branches are dendrites. So all of these are dendrites. And the center is an axon. And a center is an axon connecting it to other neurons. So this one is the axon and this one is the soma. The soma is the, let's say, the equivalent of the hidden state, as we know in a normal neuron. And you can see this as a tree. So it's like a reverse tree. These are the branches, and this is the main thing that grows from the soil. And it communicates using action potentials, which are electrical signals. And one of the first artificial neurons that have been proposed to model this would be the McCulloch-Pitts neurons that have been proposed in a logical calculus of the ideas immanent in nervous activity in 1943. I didn't expect that neural networks, or the first ideas behind artificial neural networks, would be this old. So we have here the scheme that we all know. We have inputs, we have weights at each level of these inputs, and there is an output only if the total reaches a threshold. So if we sum these and perform any activation function, and then the output is superior through a threshold, then we emit a signal or have a significant value. And any kind of mathematical or logical operation can be expressed as a combination of these neural operations. So I can have, using just these, I can represent a XOR, I can represent an OR, and etc. So let's get back a little to deep learning, from the idea from a neuron to a network. So this is what a standard neural network that we know looks like. And we have here an image, and an image actually is a matrix, or like multiple stacked matrices of numerical values, and each numerical values represents a color or a grade of a color, from 0 to 100 and 255 if we're on the gray scale, where 0 is the absence of color, so black, and 255 is like the sum of all colors, which is white. And when we feed this matrix into multiple neurons, and then we perform some activations on them, then we're going to get at the end a result which is detecting what's in the picture that says it's peppers. And there are many similarities between real neural networks and what we observe in the visual cortex. So on the left, I have a schematic of an artificial neural network. It is just the same drawing I had here. And here we have a drawing of the human visual cortex by Santiago Ramon o Cajal. which have won the Nobel, I think they were Nobel laureates in 1906, which is quite old. So the similarities are high-level structural similarities. The connections are weighted. We have weights here, the standard weights that we know in machine learning, and at visual cortex as well. We do have weights at these connections. So the black dots here are like real neurons, somas. All of them are composed of many individual units, neurons, the black dots I'm talking about. And in terms of the network structure, that is somewhat layers. In artificial neural networks, we have many layers that we define ourselves. And you can see also here on the visual cortex that we have many layers. So this one is a bit dense, this one is a bit more sparse, this one is a lot more dense, and you can see different types of neurons and layers that are structured into layers. And this is why we have a similarity of representations between CNNs and the visual cortex. Many people choose to use CNNs to model the behavior of the visual cortex, the part of the brain that's responsible on vision. So we have different layers in the visual cortex called V1, V2, V4, and IT. And they communicate with spikes. And we can model this with different layers of CNNs. And V1 can be represented by this block, V2 by this block, V4 by this block, etc. And experiments have shown that CNNs trained to do object recognition predict the activity of brain cortex on the same image. And CNN sometimes works better than actually fitting cortex data. And this is why we have this layer by layer correspondence. And what do you mean by representation? So when I say to you cat, what do you imagine in your head? Whenever you see a cat, you have like this abstract concept of a cat. You imagine like this cat idea, and that's what we try to incorporate into artificial neural networks and in their learning. And in many cases, we notice the similarity of representation. In summary of the comparisons I've done before, the brain and the real neurons and neurons in artificial neural networks have common aspects. So in terms of structure, all of them are nonlinear units and connected in a network and have plastic connections. Plastic connections means connections that change over time, which means weights that change over time. As you can see in artificial neural networks, when we are training them, we are changing the weights constantly. And changes that are aspects that are empirically observed, such as encoding the information in an analogous way, having similar representations. And in terms of differences, we have structural differences. So the brain or the real neurons use spikes to communicate, but ANNs, artificial neural networks, don't use them. The time is continuous because our brains don't stop at some point. They learn in a timely manner. We learn over time from our experiences, and we observe a lot more recurrence in the brain. It is the same idea in recurrent neural networks, and of course in terms of complexity and diversity. And the major aspect that they are different in is the learning, because backpropagation is not biologically plausible, and it's the algorithm that we use to train artificial neural networks. And the idea of having a global loss function, we don't know if the brain has like a global, or if it uses loss functions at all. Let me just go a little bit deeper into these 2 points and explain them, why it's not biologically plausible. So we have certain limitations of backpropagation in terms of doing the credit assignment. The way the weights are updated is based on the weight transport across the network. In artificial neural network, we do in the backward pass we do a weight transpose, which we don't believe happens in the brain. We have the update blocking problem. So we need to complete forward pass to calculate updates, which requires more memory and time. So when we are doing the forward pass, we are saving into memory, into our computer, into the RAM, all the hidden states, the all what we are doing, and then wait to calculate the loss and do the backward pass, which consumes a lot of memory and time, which is contrary to the brain. The brain is very simple and compact. So the idea of having a global loss function. So when we calculate the error, we're not calculating an error for each layer or for each neuron on its own. Where did it do the mistake? We calculate a global error for the whole neural network. At the end, we calculate the accuracy, like loss function that you use, maybe squared error or whatever. But it doesn't tell us about where the mistake has happened, at which level in the neural network. As you can see here, we can have a local loss function at each layer if we wanted to. And we have non-local synaptic plasticity, and the neurons in an artificial neural network get information from neurons from in all over the network, while in the brain, neurons see only the neighboring neurons. And the quest for bioplausible alternatives to backpropagation is still ongoing. So there have been many papers that have been proposed to overcome this, and I'm citing a few of them here. Some people considered using segregate the idea of dendrites, so the branches of neurons that we talked about earlier. Some people proposed forward learning with top-down feedback, which is an algorithm called Pepita, and many others. So in total, we have, when we are working in this field of NeuroAI, we have two approaches. We have a top-down versus a bottom-up modeling. So we can start by a biologically plausible model of the brain, like a biological model of neurons, synapses, and small networks. We start by that and then adjust it until we make it perform a desired function. We make it performant and improve its accuracy and performance in general. Or we can start by having our neural network that is functional on a task. So now we have our neural networks that we know they're not very, very biologically plausible, since they use backpropagation. And even in terms of structures, such as transformers, they're not biologically plausible at all, at least at some point. But we can still adjust them until we make them more biologically plausible and more interesting for people who do neuroscience. And the advent of deep learning shifted the computational neuroscience community more toward this way of thinking. And learning rules are now a lot more involved in neuroscience research. And one of the interesting aspects, and I think Wajih Ben Sheikh talked about this in an earlier presentation, the brain uses about 15 to 25 watts of power to run its billions of neurons and perform advanced cognition. So just to give you an idea about how low this is, a hair dryer consumes around 1,500 watts, if I'm not mistaken. I don't know if it's watts or kilo. Yeah, definitely it's watts. But the brain is 15 to 25 watts only. And clearly, deep learning technology has a lot to learn from the brain. And this is why neuromorphic engineering designs specialized hardware that simulates neurons and chip, and it is inspired from the brain. And these can be used for always on battery powered devices, especially in resource constrained environments. We have here a convolutional neuromorphics chip from Synsense AG, which is a company based in Zurich. And we have dynamic vision sensors that rely on spikes, and they behave similarly to artificial retinas. I don't know if you can see it, but a man is moving here. So the image is divided, the video is divided into two. A person is moving here, and this camera detects only the movement, which parts of the image are changing over time. And this is why it doesn't consume much energy. And the brain can do amazing things. So this is why we should keep on learning from it and improve our existing literature and deep learning. So it is good at out of distribution generalization. We adapt very well on novel environments. We have an excellent transfer learning, few shot learning, continual learning, you name it. Multimodal integration. So what do we mean by this? Is that our brain uses different information, not just vision images that we see, but we use our hearing, we use our senses, we use the language, all at the same time. And it performs very well in our learning. Also, we are very good at abstract planning and multi-step reasoning. And studying neuroscience and cognitive science can help us understand what is missing in AI. And there has been this cool paper that's called Deep Learning Needs a Prefrontal Cortex. And this paper came out from, if I'm not mistaken, from Joshua Benju and Jacob Russell. And it gives like directions on how deep learning can be improved. So what's next? At least what I've considered in my research is feedback alignment techniques that are use random matrix in the backward path to replace backpropagation. We have dendritic and three-factor learning, which uses the reward signal that modulates Hebbian learning and exploits complex structural biological neurons. This idea is a bit similar. It's like trying to train or to learn using reinforcement learning. We have target propagation instead of gradient propagation, eligibility traces that use an energy function, etc. It's still an active field of research. And if you are interested in this computational neuroscience aspect, then there are some books that have been recommended to me. So we have this one in Theoretical Neuroscience by Peter Dian and Larry Abbott, and Neural Dynamics by Wolfram Gerstner. And there is another one by Idzikevich that's very good. It's called Dynamical Systems in Neuroscience. It's the one that I use personally. And if you're interested in computational neuroscience and machine learning courses, then maybe you can consider NeuroMatch Academy. They have an academy in computational neuroscience, another one machine learning, if I'm not mistaken, another one in, I think, climate science or climate change, something like that. And there is Imbizo, which is a winter school. I think it takes place usually in South Africa, and it's quite advanced neuroscience compared to Trent Camina. So usually I think people would go to Trent Camina, or take this one, NeuroMatch Computational Neuroscience course, and then go to Imbizo, which is more, I think, more advanced. And that's it for our talk today. Thank you so much for listening, and I'm here up to your questions.
Okay. Thank you very much, Iman, for your enlightening presentation. So we're gonna take a couple of questions. So first question comes from me, and it concerns the explainability of bio-neural networks. As we know, ANNs suffer from challenge aspect, which is they are black box model, and there are some gaps in them. So how can we improve the explainability of bio-neural networks? of biologically inspired neural models, or do they exist independently?
Okay, so the question, if I heard well, is how can we improve the explainability of biologically inspired neural models? So there are some techniques that are, let's say, more simple and they are explainable. They are existing techniques, but they are not as complex as the deep learning models that we have currently in the literature. But I think there is, people usually just try to see what's happening, just like we have in deep learning, to see what's happening inside, like try to see the representations that have been learned, explore the neural fields, and try to explore the properties of the network. But I tried it during my master's to do some interpretability on these models, and the methods that I considered was just taking the backpropagation, like the non-biologically plausible methods, and I tried to apply them for these ones. And I think there is a need to develop more explainable um, biologically plausible methods. I'm not very familiar with the literature of the explainability, particularly for bio inspired neural networks, but I'm sure that there, like, I'm just aware of like some less complex techniques that they use, and they are way more explainable than any DNN model. This is why like neuroscientists tend to use more statistical approaches than just use a black box machine learning model. And I believe that there should be more work on this.
So the next question says, uh, in the intersection of AI and neuroscience, how much did you need to get into more theory of neuroscience and theory of AI?
So it depends on what you want to do. Um, are you trying, because there are two currents, I believe. Are you trying to use the existing deep learning to advance neuroscience? So you're not working on advancing deep learning, or are you trying to inspire from neuroscience and then improve deep learning? I myself, during my previous work, I would read literature in neuroscience. I'd read a lot of papers in neuroscience and then try to apply them to my knowledge, to my previous knowledge in deep learning. But there are a lot of papers that are in between the two, on people who just work on their AI. They are advanced on both. Because I mean, the first people who worked on these neural networks are people who like try to read a lot of neuroscience and then design them. And then over time, people became less and less experts in neuroscience. So yeah, it depends on the person and how deep you want to go in each one of them.
Okay. The next question concerns more of the hardware aspect, and it says, will bio neural networks create a new paradigm of computing as well as hardware plausible neural networks?
So yes, a lot of people have been trying to design hardware that is more suitable for these neural networks, especially for the alibi of being more energy efficient. Because if we each type of computing, like the standard neural network training scheme that we know is we have a lot of matrix multiplications, and this is why people have designed GPUs to be efficient with matrix and heavy calculations. Matrices and heavy calculations. And if we want now to have a different types of neural networks that need different, more efficient hardware, why would you want to train it on a GPU that's very good for matrix multiplication if you don't have that much matrix multiplications? Then people are designing other types of hardware that are more suitable for these algorithms. And many companies are working on this. I'm aware of the Intel chip, but I believe even IBM and other companies, Sinsens, I think Spin Cloud, if I'm not mistaken as well. So yeah.
Okay, so the next question says, NeuroAI seems fascinating, yet what's its level of readiness for actual application? And it's related to my question. So can research on biological neural networks realistically like reach the level of performance of actual NNs such as transformer-based architectures?
Okay, so transformer-based architectures are good with certain scenarios, and these biologically inspired neural networks are good with other scenarios. Each one of them has its pros and cons. If you just want performance and bigger models, then transformers are the solution. But if you don't want a very big model and you don't want to have maybe thousands of GPUs, then maybe NeuroAI is the answer for you. And there are a lot of uh, in the terms of level of readiness, of course, everything is still in development, but some people consider CNNs as NeuroAI. So a lot of people use CNNs. If we want more advanced, more real, like more biologically plausible neural networks, then people use them in simulations to understand the brain, etc. And another example is neuromorphic computing. Some people are already commercializing their chips and their algorithms, and they are deployed in many places. So still in development, but still works.
Okay, I believe this was the last question. Thank you very much, Iman, for accepting our invitation. It was our pleasure. Thanks again. And thank you everyone for coming to today's conference. See you tomorrow, inshallah, for another topic.
Thank you, everyone, and thank you, Scope AI, for the invitation. I hope I'm gonna see you in another conference.